So today we are going to discuss about the infinite potential well. So this quantum system is very important to solve many quantum mechanical problems, like complex problems, like when we are going to discuss in solid state physics the electron theory the electron theory, so free electron theory, then this kind of potential is utilized there. So this is a very common potential which the students can find in many complex problem, like in the field of solid state, material science and quantum mechanics also. So this is a very standard system, so in which we are going to discuss about some the problems, and we are going to discuss in detail the quantity like Schrodinger equation, and also the main thing like what are the implementation and what are the application of infinite potential well. So here we are going to begin. Before discussing the wave function, we should know about several things. So first we should know about the waves and its equation by which the waves are represented. So a wave is a disturbance or oscillation that travels through space accompanied by a transfer of energy. The most basic waveform equation is represented by y equals to a cos omega t minus kx, where a is the amplitude of the wave that is traveling in the space, omega is equals to the 2 pi nu and it is a angular frequency, and nu is the frequency, k is the wave vector and k is equals to 2 pi by lambda. If Vp is the phase velocity or wave velocity of the above wave moving in positive x direction, then Vp equals to lambda times nu. Thus, in terms of Vp, we can change the wave equation which can be written as y equals to a cos 2 pi nu in the bracket t minus x upon Vp. So this is the simple wave equation, and this is very important because before discussing the wave function we should know about the wave and what is wave equation and what is the characteristics of wave. Now in this slide we are going to discuss about de Broglie hypothesis and matter wave. Since wave functions are associated with the matter waves, and we should know about what are matter waves and what are de Broglie hypothesis regarding the matter wave. So de Broglie proposed that wave particle duality must not be restricted to radiation but should be universal. That is, matter particles should also possess wave particle duality. So a moving particle, whatever its nature, has wave property associated with it. So de Broglie proposed that the wavelength associated with the particle with the momentum p is given by lambda equals to h upon p. This relation called de Broglie relation, and it shows the connection between the momentum of the particle and the wavelength of the particle. So it is actually representing the wave particle duality of a material wave. So in this slide we are going to discuss about the basics of wave function. So in general wave function is called wave of probability. So where the concept came of wave function is that when the matter or material waves are coming, then the question arises that in general way in water waves, suppose for example in water waves the quantity that varies periodically is the height of water wave. Similarly in sound waves the quantity which is varying is pressure. So basically waves are defined as the periodic disturbance in a medium. So it is expected that what are the disturbance, which kind of or what entity that are varying, which causes the wave function or which causes the material wave. So in general the waves are disturbance, that is a periodic disturbance in a particular media. So when disturbance occurs it generates waves. Okay, so there are different kind of waves, like water waves. So water wave generates when the amplitude of water molecules are changing or varying. Similarly the sound wave generates when the pressure in air molecules varying. So they have supposed that what are the cause of material waves. So they have taken a concept that the quantity that varies or that forms material wave is wave function. So a wave function is a complex function which contains all the information about a quantum system and from which all the dynamical physical quantities such as linear momentum, angular momentum and energy of the system can be computed. So the value of wave function associated with the moving body at a point xyz in space at any point at any time t is related to the probability of finding the body or that object or that material particle there at that time. Since the magnitude of psi oscillates between the positive and negative value and obviously amplitude represent the probabilities, the wave function represent the probabilities. So the wave function psi has no physical significance as the probability of finding the particle at any place or any instant cannot be negative. So basically psi represent the probability of finding the particle or object in the space, and if simply we are taking psi, so psi there is a psi is acts as a normal wave. It is represented by normal wave function, normal wave equation. So psi have the amplitude positive and negative. So if psi represent the positive, there are no meaning of negative probability. So that's why only psi has no physical significance, but mod psi square is always positive value and thus is a physically significant, and it gives the probability density, that is mod psi square dx dy dz gives the probability of finding the particle at a time t in the volume element dx dy dz in space. So being a complex function, the wave function psi can be written as psi equals to a plus iv. So what is the complex conjugate of psi? A minus iv. So when we are finding mod psi square, that means equals to psi into psi star, that is equals to a plus ib, a minus ib. So when we are computing this, we got a square plus b square, which is a positive quantity. So the wave function which is represented by psi has no physical significance, but when we are talking about mod psi square, then that mod psi square representing the probability of finding the material particle in the space, and we will get the positive quantity, and that will shows the probability that how much is the probability to find the particle in the particular space at a particular time. So here in this slide we are going to visualize the concept like what is happening in infinite square well. So it is actually, if you can see in the figure, just a minute, if you can see in this figure, there is a particle, and this can be any material particle. Here we are discussing about the case of electron. So if an electron is constrained to move in this potential, so the walls of the potential is infinitely small, is infinitely long. So that electron is confined to move in between the walls. Okay, so it is constrained to move between these potential, and whatever the quantum behavior of this system, which kind of energy level we are going to get, what is the wave function of this system, this is a very important interest, and this is a purely quantum mechanical system. So you can see there, this is the whole system, like an electron which is constrained in the potential that is infinitely long. So electron can exist only in this region, and after this region, after this boundary, it is impossible to exist this electron. So in this region and in this region, the wave function is 0 because the particle is only confined in this region. So whatever the wave function of the particle, that wave function is confined only is this region, and on this boundary the wave function should vanish according to the definition of wave function. So you can see that this is that figure B is the representation of ground state wave function. Again, the figure C is the representation of first excited state. Similarly, D is second excited state, E is third excited state, and F is fourth excited state, and so on. So you can see here that wave function only constrained and only exist in this region because the particle is confined in this region, and after this region, before this region and after this region, the wave function is vanished. So here the same representation, which is representing the different states, which is the quantum state representing by n. So this is for 1D model. So if you are talking about the electron is confined only in x direction, so this kind of wave function we are going to get, and this is a simple representation of different wave function according to the different quantum state. So this is for n equals to 1, this is for n equals to 2, n equals to 3, and so on. So now we are going to discuss about the case. So consider a particle of mass m moving along x-axis between the two rigid walls at x equals to 0 and x equals to L. The particle is free to move between the wall. The potential energy of the particle between the two walls is 0, and that is there are no force acting on the particle. So we can assume the particle as a free particle because the potential energy in the well is 0. That means there are no external force on the particle. So it is free to move. The particle does not lose energy when it strikes back and forth in the potential well, because the walls are infinitely rigid, and let ux is the potential energy function, then ux can be represented mathematically as ux equals to 0 for the reason when x is greater than 0 and less than L, and ux equals to infinite for x is less than equals to 0 and x is greater than equals to L. So for this reason, which is shaded reason, the potential is infinite, so there are no probability of finding the particle, and after L x is greater than L, the potential is also infinite, so there are no probability to find the particle. Now the wave function for the particle can be determined by solving the Schrodinger equation. So Schrodinger equation is similar to the Newton's law in classical mechanics. So for quantum mechanics, Schrodinger equation is like Newton's law. Okay, so this is a fundamental equation and it cannot be derived from other any equation. So in general, the time independent Schrodinger equation can be written as d2 psi upon dx2 plus 2m E minus u, where E is the total energy, u is the potential energy, upon h cut square into psi equals to 0. So since u equals to 0 inside the box and outside there are no wave function, so we are not talking about the either outside wave of either outside of the well condition. We are only discussing in the wave function in the well. So the equation will be d2 psi upon dx2 plus 2me upon h cut square psi equals to 0. So when we are going to solve this second order differential equation, the general solution of this equation is psi x equals to a sin kx plus b cos kx, where k equals to root 2 me upon h cut square. Okay. Now if you can see the general equation, there are two arbitrary constant a and b. So according as we have discussed earlier the properties of wave function, so with the help of the properties of wave function, we should remove that arbitrary constant a and b, because that property of wave function is valid for any wave function. Okay, so one by one we are going to apply the boundary conditions. So first we are going to apply the boundary condition are psi x equals to 0 at x equals to 0 and L. This is the boundary condition which states that wave function should be 0 at plus minus infinity. So since our particle is confined in the L length, so at the boundaries the wave function should vanish. So psi x equals to 0 when x equals to 0 and x equals to L. So for x equals to 0, just putting the value at x equals to 0 in this equation, so we will get psi x equals to a sin kx plus b cos kx, that gives b equals to 0. So by implementing this boundary condition, we are getting b equals to 0. So substituting this b equals to 0 in this equation, our wave function is now psi x equals to a sin kx. Now again implementing the second boundary condition, that is the wave function is vanished at the boundary. So psi x equals to 0 at x equals to L. So when we are going to implement all the thing, we get kl equals to n pi. Since a cannot be 0 here, because if a will 0, the whole wave function will vanish, which is not possible. So sin kx will be 0. So when we are putting sin kx equals to 0, sin will give 0 value for sin n pi. So kl equals to n pi, and now we are getting kl equals to n pi after solving this boundary condition. So after implementing the wave function condition in our wave function, we are getting k equals to n pi by l, since n equals to 1, 2, 3 and so on. So now our wave function becomes psi n equals to a sin n pi upon l into x. So the subscription n is psi n means the wave function depends on n only. So the allowed energies are obtaining using k equals to n pi by l, where we have initially supposed that k square equals to n square pi square by l square, and k square equals to 2me upon h cut square n square pi square upon l. So here when we are going to simplifying this, we got en equals to h cut square upon 2m n pi upon l ka whole square. So basically our energy of this quantum system is proportional to the quantum state square of quantum state. So each value of energy En for n equals to 1, 2, 3 and so on is called the energy eigenvalue, and corresponding wave function is called eigenfunction. Thus inside the box the particle can only have discrete energy, and for that particular energy there are the allowed wave function. So in the particle confined in 1D box have the energies, they have not continuous energy but discrete energies. Now the wave function we have got from applying all the boundary condition, still there is a arbitrary constant a. So we have one property called normalization property, which we have discussed in wave and wave function and its properties lecture. So we can implement that here. So after implementing the normalization condition, according to normalization condition, integration over minus infinity to plus infinity mod psi squared dx dy dz equals to 1. So since we are here we are talking about 1D and our particle is constrained in the limit 0 to L. So we are putting the whole limit and all thing. So integration over 0 to L psi n star into psi n, this is also written as mod psi n square dx equals to 1. So just put the value of psi n. So we got a square integration 0 to L sin square n pi x upon L dx, that is sin square. So when we are going to integrate this, we got a equals to root 2 by L. So when we are putting the value of a equals to root 2 by L in our wave function, so psi n equals to root 2 by L sin n pi x upon L is the normalized wave function corresponding to the energy En equals to n square pi square h cut square upon 2ml, and this represent the wave function, normalized wave function, and energy eigenvalue for the particle which is confined in 1D box. So if we are going to draw our wave function, you can see here the energies for particular energy, particular quantum state for n equals to 1. Our ground state energy will be h square upon 8 ml square. For n equals to 2, that 4 h square upon 8 ml square, and that is 4 E1, and for n equals to 3, 9 E1, for n equals to 4, 16. So you can see that pattern that the energies are discrete, there are no continuation in the energy. So for the particle which is constrained moving in the box with the length L, having the discrete energy level. Similarly here you can see the wave functions also. So these are the representation of different wave functions, and the corresponding energies are these. Now if you want to plot the probability versus x plot, then what is the probability? Mod psi square. So we have our wave function, and so just take the mod psi square. Mod psi square means psi into complex conjugate of psi. So after doing that, we are getting this kind of plot. So from this we can find out our probability of finding the particle. So if I am taking the case ground state case, so what is the probability, maximum probability to find the particle is in the mid portion, yeah, that means L by 2. So if we are going to further, if there is a calculation that is called expectation value of position, so if that gives the maximum probability of finding the position corresponding to the position where the probability is maximum to find the particle, so that is L by 2. And if I am talking about the first excited state, then there are 2 points where the probability is maximum, and that is L by 4 and 3 L by 4. Similarly, for n equals to 3, there are three points where the probability should be maximum.